Now let us discuss the stability in the state space. Up till now, we discussed the stability only in the S domain. Then how the question arises that how we discuss the stability in the state space or with the perspective of the state space. Now we have also discussed the Eigen values of a matrix. So the Eigen values of the matrix are these are the solution of the equation. These Eigen values are actually the solution of the equation determinant of S identity matrix minus A is equals to 0, which also yields the poles of the transfer function. Now let us consider the definition of the Eigen vectors. That is, it can be written like that is Ax equal to lambda x in this case. Now rearranging this, and after rearranging we get this. To find the value of we multiply this with lambda I minus A inverse, and finally x is given by this equation. Now we see that all the solutions will be null in this case, but only if there is the occurrence of the 0 in the denominator. If there is the occurrence of 0 in the denominator, then in that very case the elements are x will be 0 divided by 0 are indeterminate. So it is only the case where the non-zero solution is possible. So in this case the value of the lambda is calculated by forcing this denominator equals to 0. So this is known as you already know, this lambda is known as the in this case these are known as the Eigen values, and x is basically in this case is the Eigen vector that we have already discussed. It is the x is the Eigen vector and lambda is the Eigen values of the matrix A. Also we found the transfer function of the system. And from the transfer function we came to know that the denominator of the transfer function has this value, that is denominator is equals to determinant of Si minus A equals Si minus A. That is, at the denominator we get the determinant of Si minus A. Okay. So as a result this determinant of Si minus A equals to 0. It is actually the characteristic equation of the system from which we can get the poles of the system. So this is the characteristic equation of the system from which we can get the poles of the system. So these two equations, this one of Eigen value and this one of this transfer function of the system, these are actually identical apart from the change in the variable name. So from these two equations we conclude that the Eigen values of the matrix A, that is, we conclude that the Eigen values of the matrix A are identical to the system poles before cancellation of common poles and zeros in the transfer function. So this information gives us, these Eigen values actually gives us the information about the poles, and we can determine the stability of the system represented in state space by finding the Eigen values of system matrix and determining their locations. So since these are identical, so these we can use these interchangeably, and as a result we can obtain the value in the S domain, and as a result we can use the stability criteria, that is the Routh criteria for that also. Now let us given a problem here. Now we have to find how many poles are there on the left half plane, in the right half plane, and on the j omega axis, like we have discussed in the previous case. So we have to calculate Si minus A. We calculate the Si minus A in this case. A is here, this one. S is the identity matrix. we find the determinant of Si minus A, determinant of Si minus A, this is, we get the value in S domain, and then we use the Routh criteria in this case. In this Routh criteria, you will see that there is actually one sign change in the first column, that is it changes from positive to the negative in the first column. So there is one sign change in the first column. The system has one right half pole and the two left half pole, because we have the three roots in this case as 3. So therefore the system is unstable. So this is how we find the stability of the system if it is given in, and this is state space representation. We need not to go to convert it into transfer function. We simply take this A and this, we simply calculate the Si minus A, find the determinant of Si minus A, and then we find this stability. Now we come to the steady state error for the system in the state space. We evaluate the steady state error for the system which are models at the transfer function. So there are actually the two methods which are used for finding the steady state error for a system in the state space. So first one is the analysis via the final value theorem, and second is the analysis via the input substitution. Now analysis via the final value theorem. Now a single input single output system represented in the state space can be analyzed by this final value theorem. It can be analyzed for the steady state error using the final value theorem and the closed loop transfer function. Now let us consider that the closed loop transfer function be represented in state space as this. Now we note that the Laplace transform of the error is given by this. From the block diagram that we have observed in the block diagram case, the Laplace transform is given by this, and Ys is equal to Rs into Ts also. There where Ts is the closed loop transfer function. Now substituting this into this, we get Es error, Es in this case. Now we have Rs1 minus Ts. Now we also know Ts is basically the transfer function, and we have calculated the transfer function in this case in the previous module also. This transfer function is equals to Ys Us, which is equals to Cs minus A inverse B plus D, that we have calculated from in the state space representation. So substituting this and using the final value theorem, that is final value theorem is limit of SES S tends to 0, that is it would be that is final value theorem is T Et S tends to infinity equals to limit of S tends to 0 SES, which is given by limit of S tends to 0 SRS1 minus Cs minus A inverse into B. So this is how we calculate the error in the state space. Now we have a problem. We have to calculate the steady state error in this case for a unit step and unit ramp inputs. Now we substitute the values, all these values in the previous equation in this equation, and finally we obtained this. We have to substitute for we have to do it for the unit step input and unit ramp input, and finally we get the value of E infinite as E infinite, which is equals to limit of S tends to 0 SR S into 1 minus S plus 4 divided by S cube plus 6S square plus 13S plus 20. So, and finally when we multiply this and we get the final equation. Now we have to do it for different cases, that is for the unit step input. So we have to find the steady state error for RS for the first case. For the first case, RS in this case is 1 by that is unit step input 1 by S, and for a second case it is 1 by S square, and for RS 1 by S the value of the E infinity in this case is 4 by 5, and for 1 by S the value of E infinity is infinity. So that the system behaves like a type 0 system. This is how we calculate the stability of the system. However, another method which is used for steady state analysis avoids taking the inverse and can be expanded into multiple input and multiple output system. Actually it substitutes the input along with the assumed solution into the state space equation, and it was first proposed by Hostetter in 1899, which was the input substitution method. That is input substitution method. Now in this input substitution method, it is used it actually avoids taking inverse and can be expanded for multiple input and multiple output system. That is, it avoids taking inverse, that inverse is avoided in that, and it can be applied for multiple input and multiple output systems, and it substitutes the input along with the assumed solution into the state equations, and it was first proposed by Hostetter in 1989, and this is the input substitution method. So we have two methods: analysis via the final value theorem and then input substitution method. Now this is all about the how to find the stability using the state space. Thank you very much.